Before we can continue talking about the universe itself, we actually need to delve a little bit more into physics, specifically what is known as the general theory of relativity. So the eventual fate of the universe itself is going to be tied to the shape of the universe. I realize shape of the universe doesn't make sense yet, but let's talk a little bit about general relativity. So the theory of general relativity was actually first published in 1915, and it states that what we interpret as gravity is actually a consequence of mass distorting the fabric of space-time. One of the assumptions or conclusions of general relativity is that space and time are not actually separate entities, that somehow they're actually mixed together in what is sometimes referred to as the space-time continuum. If you've ever heard of that phrase before, this is where we get that idea. So one way of thinking about space is like a giant trampoline. Okay, so we have a giant trampoline, and if we put something on it, then you can see how the trampoline curves and bends. Well, if we then try to throw something like a marble past the big heavy object in the middle, as it goes near it, because the trampoline itself has been curved, the object has to follow that curve of the trampoline and will therefore curve around that object. This is kind of how we interpret space and time. Now, this is not a perfect analogy. A trampoline is essentially two-dimensional, whereas we're trying to figure things out in a 3- or 4-dimensional space. Don't worry about it. Don't think too hard. I've given myself so many nosebleeds over this. But the idea is that objects have to follow the curvature of space. So, because of this, what this states is that acceleration and gravity are actually the same thing. That it is impossible to distinguish the effects of gravity from the effects of accelerated motion. So, what this means is as an object is accelerating up, to an observer inside of that, it would appear as though gravity was acting. So, for example, in this case, we have a rocket ship that is accelerating up at 10 meters per second squared. If you remember way earlier in the beginning of the semester, we mentioned that the acceleration caused by gravity at the surface of the Earth was about 10 meters per second squared. Well, because this rocket ship is accelerating up at 10 meters per second squared, if the observer were to drop something, then from her point of view, the object would accelerate down at 10 meters per second squared, which is exactly what she would see if she was on the Earth doing the exact same experiment. So one of the strange conclusions of general relativity is that acceleration and gravity are actually the same thing, that there's no way to distinguish between the two. This is what is known as the principle of equivalence, or the equivalency principle. Local observations made in an accelerated frame of reference cannot be distinguished from observations made in a gravitational field. Gravity and acceleration are the same thing. Now, what this means is because of this, we're going to see some interesting things happen in an accelerated frame or in a region of gravity. So remember, acceleration and gravity are the same. So in this case, we have a small hole on the side of the rocket ship. We then throw a rock or shoot a bullet through the hole as the rocket is accelerating. As the rocket accelerates up, then the bullet, which is following a straight line path, remember Newton's laws, no force means no acceleration, the bullet is going to go in a straight line. However, because the rocket is going up, it's going to hit much lower than the hole that we just shot the bullet through. Now, this is one frame of reference. This is the frame of reference of the bullet. Now, if we change perspective and we imagine that we are sitting in the rocket ship, then, from our perspective in the rocket ship, we see the bullet enter and then bend downward, just like we would see for gravity. If you throw an object horizontal, it actually curves downward because of gravity. Well, this shouldn't just work with bullets and rocks, it should also work with light. As the light enters through the hole, it wants to travel in a straight line. But because the rocket ship is accelerating up, we see that it actually lands at a point lower than directly across from that hole or window. Now again, change frame of reference so that we are sitting in the accelerating ship, and this means that we should see a bending of that light. So, what we can conclude from all of this is that gravity should be able to bend light, or at least a curvature of space should lead to a bending of light. And this is exactly what we see. There have been several experiments during total solar eclipse. A total solar eclipse is where the moon completely blocks the surface of the sun, and we see that the stars that were behind the sun from our point of view, so normally we would not be able to see these, their light has been bent, so as we look at them, they actually appear to be just on the side of the sun. This is what is known as gravitational lensing. So, because we have a massive object, light has bent. All right, here is our fourth clicker question. According to Einstein, what causes the acceleration we interpret as gravity? A, the curvature of space caused by mass. B, energy from quantum particles. C, energy from the exchange of photons between objects. Or D, the mutual attraction of all objects of mass. Go ahead and think about it, and we'll discuss in just a bit. All right, so according to Einstein, the acceleration we interpret of gravity is actually caused by A, the curvature of space. If you remember, when we have a curved region of space caused by mass, then objects that go through that curvature are going to accelerate, and acceleration and gravity are the same. So what we interpret as gravity is actually an acceleration caused by the curvature of space created by mass. Yeah, I realized that was a mouthful and it was confusing, but the correct answer is A.